To define linear regression, we need to understand what we're trying to minimize. The word is called here loss function, and the loss function is the amount of residual error we obtain after fitting the linear function as good as possible. The residual error is the sum of our training examples, j, of phi j, which is the target label, minus our prediction, which is w1xj minus w0 to the square. This is the quadratic error between our target labels and what our best hypothesis can produce. The minimizing of loss is used for linear regression or any regression problem, and you can write it as follows. Our solution to the regression problem, W star, is the arc min of the loss over all possible vectors W. So the problem of minimizing quadratic loss for a linear function can be solved in closed form. What I will do is, I will do this for the one-dimensional case on paper, and then I'll also give you the solution for the case where your input space is multidimensional, which is often called multivariate regression. We seek to minimize a sum over quadratic expressions where target labels are subtracted with the output of our linear regression model parameterized by W1 and W2. The summation here is over all training examples, and I leave the index of the summation out if not necessary. The minimum of this is attained at the place where the derivative of this function equals 0. So let's call this function L. For the partial derivative with respect to W0, we get this expression over here, which we have to set to 0. We can easily get rid of the minus 2 and transform this as follows. Here, M is the number of training examples. Now this expression over here gives us W0 as a function of W1, but we don't know W1. So let's do the same trick for W1 and set this to 0 as well, which gets us the expression over here. We can now plug in the W0 over here into this expression over here and obtain this expression over here, which looks really involved, but it's relatively straightforward. With a few steps of further calculation, which I'll spare you for now, we get for W1 the following important formula. This is the final quotient for W1, where we take the number of training examples times the sum of all xy minus the sum of x's, sum of y's, divided by this expression over here. And once we've computed W1, we can go back to our original articulation of W0 over here and plug W1 into W0 and obtain W0. Let's just do this. These are the two important formulas that you can also find in the textbook. I'd like to go back and use those formulas to calculate these two coefficients over here. We get 4 times the sum of the xy's, which is minus 32, minus the quarter of sum of x's, which is 18, and the sum of y's, which is minus 6, divided by the sum of xi squared, which is 86, times 4, minus sum of x squared, which is 18 times 18, which is 324. And if you work this all out, it becomes minus 1, which is W1. W0 is now obtained by computing a quarter times sum of all y, which is minus 6, minus W1 over 4 times sum over all x. And if you plug this all in, you get 3 as over here. So our formula is actually correct. So here's another quiz for linear regression. We have the following data. Here's the data plotted graphically. And I wonder what the best regression is. Give me W0 and W1. Apply the formulas I just gave you. And the answer is for W0, 0.5, and for W1, 0.9. If I were to draw the line, it would go about like this. It doesn't really hit the 2 points at the end. So if you were thinking of something like this, you are wrong. If you draw a curve like this, your quadratic error becomes 2, 1 over here and 1 over here. The quadratic error is smaller for the line that goes in between those points. This is easily seen by computing as shown in the previous slide. W1 equals 4 times 118 minus 20 times 20 over 4 times 120 minus 400, which is 0.9. This is merely plugging in those numbers into the formulas I gave you. W0 then becomes a quarter times 20. Now we plug in W1, 0.9 over 4 times 20 equals 0.5. So this is an example of linear regression, in which case there is a residual error, and the best fit curve is the one that minimizes the total of the residual vertical error in this graph over here.